limit. That's gonna be tough. You know how postponing works? There's always something else that basically is gonna get it pushed again. It's always a problem. And postponing doesn't work very well. Probably what I'll do, but I've been looking at, we might change a little bit how we're gonna do the second phase. In terms of timing. What the heck? Somehow this computer is doing spring break. Okay, cool. Okay. All right, good afternoon. While my computer is still getting back from spring break, somehow it seems to be stuck somewhere, so I'm rebooting it as we speak. A couple of things that I want to talk about first. Definitely for those, I guess, those of you who are here have probably finished most of your simulations. But I just got a message from our computer support group that some people are running simulations that have been running for more than 6 hours. That's definitely not the intention, and it obviously means that there's something wrong with your simulation. That you either are running over way too long a time period, or that you're basically messing up a little bit your time steps and so on and so forth. So keep an eye on your simulation. That's for those of you who are watching over webcast. Check how long your simulations have been running, and if they've been running longer than half an hour or something like that, probably wise to basically kind of cut them down. Otherwise, I think we're killing off the machines, all the machines, and nobody gets anything done as a result of that. So please, I'm going to send a message, email message to all of you as well. Manage your time. Simulations of 6 hours for this type of thing do not make sense. And that's true for everything in some senses. Yeah, you can run very complex long simulation, but very often it makes sense to think a little bit about what should I simulate, and from that simulation, what can I extrapolate. There seem to be also quite a number of people who have some problems with the power analysis and doing so. There's a couple of ways of doing this. One way, obviously, is to do the full simulation and take the average current. But in a sense, it's a more intelligent way of looking at it is look at your nodes in your network, look at the fan-out, estimate the capacitance. From your analysis, higher-level analysis of activity, you can figure out what the basically switching activity is on different nodes, multiply the two together, and you get a first shot. I'm happy with power estimations within 15% accurate. I'm perfectly happy with that. It's not like timing where you have to be smack on or the thing doesn't work. It's more like getting an estimate of approximately where your power dissipation should be at, and that should be fine. So don't overdo this. Also, if you kind of get totally stuck, very important is, I haven't mentioned this yet, but I think you can keep on working and trying to get things better and closer and things like that to the last minute. Right? You know, when something is due at 5 o'clock, you simulate till 4:59, and you try to get the best possible or the closest result of that. My vision is that actually this reduces the grade you're going to get. A good report is more important. So very often with every report or every project you're going to do in life, it's worthwhile to say, okay, certain point in time, this is the deadline. I'm so far away from the deadline, I'm going to basically say, that's it. I'm done with basically my analysis work, and now I'm going to spend my time on the report. Because you can do the best in the world, doing a lot of analysis, a lot of stuff, but if you cannot explain it and you cannot put in a report, nobody will ever know. So it's waste. So spend your time on your report, making sure that you say, here's what I've done, that's why I've done it, and yes, there might be other things I still can do, but that's where I am. That's just as important. So don't overdo it, I think. Like always, plan your time wisely. That's the key message I want to bring. So good reports are absolutely essential. I'm still trying to get this thing. Okay, talks. Courses. We're getting close. SO8. Okay. Oop. I hope I'm opening the right file. Okay, good. Oops, that cannot be. Okay, so there's another thing that I promised you last lecture to come back to, and I haven't forgotten. Let me just see if I can get this thing to synchronize. Oops, that's something else. I don't need that. And Microsoft is not happy either, so let's send it a report. Okay, so let's me first come back to this issue that I had a clear answer on last lecture. It was about the level restoration in pass transistors. Remember that? The different modes. So let me sketch out a couple of things you could do. Remember the level restoration problem? You have a pass transistor network, purely NMOS, The NMOS only can get you to VDD minus VT, so we find a way to add some feedback to it, to the circuit in such a way that I can pull the node all the way up to VDD. So the first technique that we showed you, let's say here's your input of your pass transistor network. You have your level restoring, or you have your regenerative inverter, and we add a PMOS to the chain. That's the standard level restorer as we know it. Now there's one problem, however, with this that you might imagine, that suppose I get a fairly large fan out of this. Right? Let's say I get a fan out of 4, or quite a bit of capacitance. It means that you will see that this node, the output node here, will take some time to get to its, so this goes up and gets to VGD minus VT. Right? This node, this will basically make this inverter trigger, so you would expect this thing to go down. But the slope and the time it's going to take before this thing really gets to the point where you turn on the VT is going to be depending on the fan out. So the load factor will slow this down. And as a result of that, it will take a while before this node finally goes all the way up to VDD. Okay, because the slowness of this feedback loop. So what people often do is the following thing. It's a very common approach. So we're going to take that apart at the expense of some extra capacitance at this intermediate node. We still have this inverter, but we're not going to use the feedback from this inverter. But what we're going to do is add a tiny little inverter in between, which just drives that PMOS transistor. So this is a really minimum size device. It doesn't drive any capacitance because the only thing it drives is a single PMOS transistor. So we can make this small, low current, low capacitance at this node. And it gets around the delay and the fan out of this output node. Okay? So that's the second approach of dealing with level restoration. You can see that the level restoration loop here, in this case, is going to be really fast. Okay? So that's approach number 2. Then the third approach I sketched also in last lecture, very briefly, when you have differential. So, okay, well, if I have differential, I already have the inversion somewhere sitting there. So what I could do is I have my level restoring devices. It's a PMOS and another PMOS. And rather than connecting this to the output of this inverter here, I know I have the inverted signal here anyhow. I'm going to connect this to here, and this guy connects to here. Right? So this also gets around the long delay of the fan out of this device. And in a sense, it's better than this technique because here an inverter is a PMOS and NMOS. Here the only load I have is an extra PMOS on this internal node. It provides some cross-coupling. Again, this is a feedback-based approach. Now I can go one step further and say, okay, this works in one direction. What people also have done, which is not as fast, but actually gives you stronger feedback and works in both directions, is something like this. So this is your pass transistor network sitting here, pass transistor network is sitting here. And what we do is now just cross-connect the two MOS transistor, the two CMOS inverters. Works as well, adds some more capacitance to it, but it has the advantage of having a really strong feedback loop. Well, one feedback loop gets open, the other one gets shut off. Now, this structure might look familiar to you. We haven't talked about it yet, but some of you might have already seen it in some other stage of your life. You know what this is? This latch. That's right. It basically becomes a latch. So one of the advantages of this structure is that I now start actually building a latch into my logic network. It has memory. If I now add some switches, and if I now add another switch here and the switch is off, the data at the output will be maintained. Which is interesting. For instance, remember why we were using pass transistor logic, where pass transistor logic was very popular? Is in FPGAs, the lookup tables. Now lookup tables were nice to have a latch to it, so you actually could use the latch that you need anyhow to help you to provide level restoration. And that's where this structure is quite popular. Okay? There's some other approaches to providing level restoration which are even more sophisticated. I'm not going to talk about those. If you I'm quite happy if you understand those four here. Okay? All right, any questions, by the way? Any questions on the project, things that kind of bother you, things that you say, boy, I haven't got a clear mind on that one yet? I know that a bunch of you had questions, and Mike has actually done an excellent job of trying to respond to them as much as he could. But let me know if there's any questions. We'll try to answer them. Yes? Yes, it's very hard. It's very hard to do this because if you look at it, the power dissipation, there's two parts, right? Obviously, there's the traditional dynamic power, and that's easy to compute, right? You have capacitors on every node. One goes up, the other one goes down. You're done. The real problem is that in the middle, while you're doing the transition, it's this time that they fight each other, right? You have a flip-flop which is in one state, and you try to force them into the other state. And while in that period, all your transistors are going to be on. So you get a lot of direct path current flowing through the structure. I would say, for the time being, ignore this. Right? Don't worry about it. Okay? But yeah, you can imagine that it says when they're sitting in the middle and waffling as, should I go left, should I go right, should I left, or should I go right? It takes some time to get there. So, but ignore it. Because it's, if you try to solve it, it's complex. It's a very hard question. Not easy to answer, analytically at least. Okay, having said that, let us get back to some other issues. Okay, so as I said, life doesn't let up. It's we're now week number 10, which means that we have another approximately 5-6 weeks to go. So and it's going to be hectic. It's and the pace is picking up a bit. So project phase 1 is due today, this evening. We have a midterm next week, 6:30 till 8 p.m., and it will be held in 105 North Gate. Same style as before. It's got open book. I will make sure this time around, last exam was a little bit kind of a fast-paced exam. I'll lower the pace a little bit on this one, give you a little bit more time to go to the questions. What it's going to cover is basically everything we've seen so far, including today's lecture. So today we're going to wrap up Domino, dynamic logic. That's going to be the end. Then I'm going to go into power and sequential. That's not part of the exam. Okay? So everything which is dynamic logic. Now obviously the material which was covered by the first midterm is fair game in the second one as well. But in reality, most of the focus will be on everything. Remember where we stopped? We had the inverter. We had done the transient analysis of the inverter. We had excluded power. So that's where we're starting, at least in terms of new material. And that it goes all the way to the different logic styles, complex logic, CMOS, ratioed logic, pass transistor logic, dynamic logic. Okay. There's a homework due, also somewhere, which is on Friday. And then there's a review session. I plan to do like last time around. We're going to have a review session next Tuesday. I'll tell you exactly what time and what place. We're going to do the same thing as before. What else is there? The second phase of the, I'll give you a little break. Second phase of the project, we'll try to start up somewhere over the weekend. And I might give you a little bit more time. I'll basically balance it out a little bit, see how things work out. Okay? So that's what's going on in terms of work. As I said, you know, the second half of the semester, beginning you get familiar with the thing, you do the little labs and so on and so forth, and then suddenly that's when the work starts. But I think it's going to be interesting because now you've done the first phase, and there was not much. excitement in the first phase. Well, there's a lot of excitement to get it work, but I didn't give you a lot of freedom yet to do weird stuff. Now, second phase, it's your turn to really come up and say, no, you start understanding what's going on here, say, hey, I can do this a lot better. So that's what I would like to see from you guys, basically coming up with some interesting alternatives of the structure you've done so far. Okay? And we're first going to do this purely on paper, or basically using MATLAB. Higher level equations. That's what I'm looking for. Okay? Alrighty. Cool. So what we're going to do today is wrap up, first of all, the general issues. Yes? Yeah, that's true. I have the room from 6 to 8. Would anybody have a problem running it from 7 till 8:30? I don't have particularly a problem either. I'll send an email around. Oh, you have a 9 o'clock. Yeah. That would be great, because, yeah, I cannot see, starting to do exams at 10, I think the intensity kind of goes down a little bit. You have a glass of wine first, and yes. No lecture on French. The room is too small. That's the real problem. If you bring everybody in the class, it just makes the room, I don't have enough space here. And getting another classroom in that same time slot is impossible. So that's why I typically move it to the evening. So I'll see what I can do with 7. Yeah, good. Alrighty. As I said, what we would like to do is wrap up dynamic logic. What we did at the end of the last class is, first of all, explain the concept of dynamic logic. And then I started to discuss some peculiarities, some specific issues of dynamic logic. And then what I'm going to do, I'm going to finish this up, and then what I'm going to do is talk about one very popular style of dynamic logic. It's called domino logic, something which has been used very extensively. And you will see why we need a logic style like domino logic. And then I'll move into, for the time that's left, talk a little bit about power again. And from there on, once that's done, next lecture, I would like to start moving into sequential logic, talking about registers, latches, and so on and so forth. Once we have those two, then we can do a lot of fun stuff. Okay. Good. Let's kind of revisit dynamic logic a little bit, just to get you the idea again of what is going on. So dynamic logic is like ratioed logic. What we're trying to say is, hey, CMOS is good, but you have a PMOS network and an NMOS network. And the problem with that is that you get, as a result of that, larger capacitance, or it hurts the logical effort. Because every time I have to drive an NMOS and a PMOS transistor. So like in ratioed logic, you say, well, I'll get rid of the PMOS network and replace it with a load device. Single load device that helps us to pull the output to high when the NMOS network is off. The problem with that is that now ratioing means that you have to ratio the transistors. You have to basically determine the sizes. That's one. Number two, you have to be very careful about the propagation delay, because now that load device is responsible for the low to high delay. And thirdly, the static power dissipation. And static power dissipation is something we don't like at all in complex MOS logic. So the idea of dynamic logic is to get around all those concerns and still have the benefits of ratioed logic. So what we have is a single NMOS network, like before, like in ratioed logic, which we call the pull-down network. And to that we add two transistors, a pull-up device, which you can look at it as a load device, and a enabling transistor, ME. And the trick that we're using to make this different and solve the problems of ratioed logic is that we're going to separate the time when we do the evaluation, when we create a 1, and when we create a 0. Okay? We're going to have two phases. In the first phase, the load device is turned on and pre-charges the output node to VDD. During that time, this transistor, evaluate transistor, is off, so the pull-down network is disabled. We get a clear 1 at the output. We charge up the capacitor. That's all we do. So the pull-up device is responsible for the 1. Then in the next clock cycle, what we call the evaluate cycle, we turn on the evaluate transistor. And dependent upon the input signals, this PDN will either be disabled or enabled. When it's disabled, nothing happened. The output stays at 1. So we're fine. No power dissipation, no nothing. We have 0 propagation delay also, which is kind of cool, right? A gate with 0 propagation delay. It's already there. However, when you have a 0, when the pull-down network is enabled, we're going to discharge the output node to this pull-down network and basically create a 0. Okay? So that's the whole idea. And as you can imagine, this is, in general, a very fast logic style. The logical effort is better than in traditional CMOS type of device, even though we added an extra device in the pull-down network. But as we will see later, we don't always need it. Sometimes you can get rid of it. So that's going to make your logical effort even better. Okay? However, you have to be aware of certain things. If you look at my inputs of this thing here, when I enable this and I say, okay, I turn this device, suppose that all of those things will be, let's take this network for instance, let's make this 0, make this 1, 1. You pre-charge this to high, then I turn this on, both of it are 1, so we're going to start discharging. Suddenly, if my input would change its mind, it say, oh, no, I don't want to be a 1, I want to be a 0. You're toast. Right? Because I have discharged already part of my output node, suddenly I turn off B, the discharging stops, but it stops somewhere in the middle. And there's no way I can get this output node back up to VDD. So what this says is that during evaluation, during eval, the only transitions that are allowed at the input nodes of the network are 0 to 1 transitions. You never can have a 1 to 0 transition, because that basically messes up the whole thing. Okay? So that's a very important rule. During eval, either the inputs stay constant, they stay at 0, or they stay at 1, or they can make a move from 0 to 1. And that's going to be very important in a minute when we start making more complex structures. Okay. At the end of last lecture, we showed some of the issues that we can have with dynamic logic. One of them was charge leakage. Obviously, when I store some charge on a capacitor, and I let the capacitor sitting there for a while, that charge is going to leak away through subthreshold currents and diode leakage currents. So dynamic logic will have a minimum clock frequency. You're going to have to clock it at a regular rate, otherwise the charge leaks away at your output node, and something that was a nice 1 starts leaking away and suddenly becomes a 0 or something we don't know what it is. How to get around that? As I showed you last lecture, I might have a slide on that, or I might not have. No, I don't. Is to add at the output node, let's say here's my output device here. This is the pre-charge device. This is my clock. In parallel with this device, I can add another PMOS transistor with a small inverter and connect these things together, and you have a level restoring device. Just like we did with the level restorer. I take the output, I feed it back, and when this thing is 1, this is 0, this PMOS device goes on. And it's not purely dynamic anymore, because now I have this small device kind of putting the output all the way up to VDD, even when it really should be floating. Okay? So using a level restorer or a bleeder can help to basically deal. So since leakage is increasing in more and more in scaling technologies, think about 65 nanometers, 45, 32, leakage is getting more and more. This has become essential. I don't know anybody with a sane mind that does dynamic design and doesn't use bleeder devices. Or you have to be extremely sure of yourself. Okay? And you have to take the risk. Okay, so that was first problem, charge leakage. The other problem that I discussed way at the end of last lecture, it's about 2.5, almost 2 weeks ago, was the problem of charge sharing. When you start playing with charge, like we do in dynamic logic, you have to be careful. Because charge can be shuffled back and forth, and when it changes charge, we change the voltages. And I showed you this simple example of a CMOS, of a dynamic gate, where you have, let's say, this node is pre-charged to VDD. It's an AND gate. And we assume that this node was basically at 0 to start with, previous history. And during evaluation, this stays at 0 and this goes from 0 to 1, which, by the way, is a legal transition. Remember, 1 to 0 we cannot allow, but 0 to 1 is fine. What's happening? Well, you can see that this transistor is off. What this transistor A does here is connect both nodes together. So you have one capacitor. So what I really get is a situation where I have capacitor CA and I have capacitor CL connected to each other. Now initially this has a voltage over it which is equal to VDD. This has a voltage equal to it which is equal to 0. Okay? Now I connect them together. What's going to happen? Well, we're going to reshuffle the charge. We're going to redistribute the charge, as we call it. Okay? So it's fairly easy to compute what the resulting voltage is going to be. So at time 0, the total charge is going to be CL times VDD plus 0 or CA times 0. Okay, that's my total charge I have initially. And in the end, we're going to distribute that whole charge over both devices. So we're going to get CL plus CA times Vx, where Vx is the final voltage. And then computing Vx is not hard. Vx is equal to CL times VDD over CL plus CA. So we get a capacitive divider. Okay? And now, depending obviously about the relative sizes of CA and CL, we're going to get a voltage drop. If CL and CL will be exactly the same, the voltage would drop by half, which fortunately will never happen because the capacitance at the output node typically will be higher because of fan-out than the capacitance of an intermediate node. But if you look, let's say, at a more complex network like this one here, this is a very typical gate. In Domino logic, this is actually one which is taken straight from an adder. And you can assume that the output capacitor is 50 femtofarad, and the intermediate nodes have 15 femtofarad of capacitance. You can see that in the worst case, I might have this capacitance and this capacitance sharing with the output capacitance of 50 femtofarad. Obviously, it's going to be impossible to add all those 15 farad. If you look at the logic situations I can apply, you would say the first case, well, I take 15 farad here, and 15 here, and 15 there. That's 60 over 50. Boy, that would be bad. But that will never happen. Because typically, I always will enable only one path to this particular logic. But the worst case is, in this case, that I would get 50 femtofarad divided by 50 plus 30 is 5.8. Which is still a fairly large voltage drop and might make your circuit start leaking and do all kind of weird stuff. Okay? All right. So that's a problem. And fortunately, it's a problem which is something you can evaluate. It's something I can simulate in advance. I know exactly approximately what the capacitance is going to be. I know the logic levels. So I can figure out what I can do about it. And if I see there's like a case like this, I should take some precaution. I should change my circuit a little bit to make sure that we're not going to run into trouble. Now, before I show you some examples of how to deal with this, one more thing I want to mention to you. I showed you this very nice analysis here, right? Very clean, capacitance before, charge after, all done, I get my voltage. This is a nice analysis, but it's not always correct. I forgot one thing. What did I forget? When I just said, here it is, I close my switch, this is the situation after I basically have turned on transistor A. Body effect is indirectly. That's an indirect factor. It plays. Body effect is right. but it's not the primarily thing. Body effect will impact it, but it's not the primary thing. What does body effect impact? Threshold, right? So we're getting close. So where would threshold enter here? Remember, this node sits as VDD. If I turn this transistor on, what would be the voltage at, without charge sharing, what would be the voltage level, that the maximum voltage level I can get at node CA? VDD minus VT. So if now my charge sharing effect is going to be smaller, this thing will be only a full closed-loop transistor when I basically have a voltage which is going to be larger than this VDD minus VTH. Then I can consider a closed case. In the other case, I cannot. I have to take into account that the maximum voltage I can get here is VDD minus VTH. So actually, you have to be careful when you do the analysis. When transistor, you have the same case here, right? This is exactly the same analysis, the same study. This is pre-charged at VDD. This is node X. If we have to actually, we don't know in advance what Vx is going to be like, right? That's an unknown. Again, this is a nonlinear circuit, so what I'm going to do is toss up a die, or basically toss up a coin and say, well, maybe the voltage is going to be larger than VDD. The final voltage is going to be larger than VDD minus VTH. So that's one case. And in that case, the transistor MA is going to stay on. It's not going to turn off. And the case, however, when MA turns off, we're going to have incomplete charge sharing. And you have to look at both cases here. So in the case that the voltage drop is going to be smaller than VTH, we're going to have this equation here. You have complete charge share. In the case of incomplete charge share, the QCA is going to be VDD minus VTH times transistor CA. That's the transistor charge on this thing. And we actually see that the equation is a little bit different. So it really depends upon how large the ratio, it really depends upon the ratio of the capacitances. If your voltage drop is going to be smaller than this VTH value, you will get a different answer than when the voltage drop would be larger than the VTH value. And then once you know this, you pick formula 1 or you pick formula 2 to basically figure out which one works. But you have to be aware of that. That this is not an ideal switch, but sometimes you have that VTH particular problem sitting there. Okay. Solution to the charge sharing problem. So what I can do now is I build my complex logic gate and I evaluate the different nodes and the different input patterns and say, there's no problem. I can sustain a voltage drop of 0.3 volt or whatever it is. I don't care. Then you don't do anything. But suppose I have the case that I showed you before, that you get a drop to 5.8. Then I worry, because I feed this into an inverter behind that. That inverter is going to be somewhere in its middle state. It's going to leak like hell, and you won't get a nice output. So what can I do? Well, one thing I can do is ensure that nodes that are critical are not at 0 when we basically start the evaluation, but at a VDD. So what I can do is during pre-charge mode, I can not only pre-charge the output node, but I can also pre-charge some critical nodes within the network. Like in this case, I say, hey, this is a problem node. If I have 0 charge on here and I close switch A, I'm going to have charge distribution here. If I put this thing at VDD at the start, and this is at VDD at the start, I don't have any charge sharing. We're done. Okay? So solution to charge sharing is basically using this internal pre-charging of the nodes. The other thing that can help a bit is to add your keeper. You have your keeper already there anyhow, or this level restorer. So suppose now I start my evaluation period. My voltage drops a bit because of charge sharing, but then the bleeder kicks in, because remember, the evaluation network in that mode is still going to be off. There's going to be no current flowing to ground. So the keeper will gradually pull it back up to VDD. So if we wait long enough, it actually will get back in good shape. So it could be the combination. And it can help in adding some pre-charge nodes internally. Okay? Here's another interesting exam problem. actually I've had this a bunch of times in the past, is clock feed through. Another effect that we see happening is very much the same as charge sharing, almost identical, but it always seems to be throw people off their feet one way or another. I don't know why. What is clock feed through? Well, you have your logic network here, and again I have a output which is floating. So what's now happening when I start evaluating? In the beginning of evaluation, so I pre-charge, this goes to VDD. In the beginning of the evaluation phase, I'm going to switch my clock from 0 to VDD. Okay? Suppose now that this transistor is off. What's going to happen with the output node? If I assume that I have a gate to drain capacitance of this PMOS device, what's going to happen with your output node, do you think? Right. So this network, the bottom level network, is off. This is pre-charged, it's floating capacitor, and I turn on my clock system. So I turn off the PMOS. I assume that it happens instantaneously, that I have a clock with a nice sharp edge, and bingo. What do you think that the output node will do? It's right there on the other side, so you should be able to read it. It's going to go up, right? Now, why should it go up? Well, it's again a charge sharing problem, right? So what I have, and it's not very hard to solve it. So you have here a node which I called CLK. It's coupled by a capacitance to node out. And that capacitance is CGD. And I have here, let's call the CL. Okay. Initial values is that this node will be at 0, this node will be at VDD. Okay? So it means that both capacitance CGD and capacitance CL will have a voltage over them which is equal to VDD. They're both charged. Now, when I raise this node from 0 to VDD, what's going to happen is that I'm going to start pushing some of the charge of that capacitor onto the output node. Well, actually, what's going to happen is the total charge on this node V out has to remain exactly the same. So we can write the equations. Initially, I have CGD plus CL times VDD. Right? That's my initial total charge I have sitting right here at this output node. In the end, I will have a capacitance which is equal, or a charge which is equal to V out, or Vx, I don't know what V out is going to be, Vx minus VDD times CGD plus Vx minus 0 times CL. Right? Vx is my final value. When this goes from V out to Vx, from VDD to Vx, this will basically have a total capacity which is equal to Vx times CL. But here you can see that by raising one node, I'm going to have only Vx minus VDD over this capacitance CGD. If you solve this for Vx, we'll find a voltage which is going to be higher than VDD by a certain fraction. Okay? And you will always see this. In dynamic logic, you will see your output signal. When nothing happens, you think it's going to stay at 1. It will go up. And you have to be a little bit careful because you don't want to go it too high, because it goes more than one diode, then we start running into trouble again and start injecting charge in the substrate. Okay, but this is a very typical effect that you have to be aware of. It's something that, and it's very easily computable because, as I said, it's pure charge conservation again. Okay? And here's a typical example of charge feed-through or clock feed-through. This is even the case when the network goes on. You see, we're staying at VDD. We turn on the clock rather than basically going down right away. We first see the output going on, and then the NMOS network kicks in, and we start pulling down. And the same thing in the other direction. So both of those effects are basically clock feed-through. Now, before we go to one last problem, this is another thing that a problem that Simone really likes. He thinks it's the most funny thing in the world, for one reason or another. It's called backgate coupling. It's a very weird thing. You might not even expect it, but you expect typically say, well, gee, this is a scary node, right? This is the node that we worry about. It's a dynamic node. It's a high impedance node. It's floating. Any kind of stuff that goes on couples right into that node. But typically, if we always expect the bad stuff to happen from coming at the input network or from some neighbors that capacitively couple in this node. But here's a case now where the effect runs actually backwards through the network. Typically, things go forward from input to output. Here's an effect that goes from output to input. Suppose I have here a nice dynamic gate, dynamic NAND gate, and I say, okay, I'm going to follow this by a static NAND gate. Right? This gate you must recognize 2 NMOS in series, 2 PMOS in parallel. That's a CMOS NAND gate. Okay. So during pre-charge, this becomes out equal to 1. This output node must be equal to 0. Okay. Now, so this is at 0, and remember there's some capacitance here. Suppose now suddenly that input 1 here decides to go to, so we have 1 here at the 1 input, 1, 0, the 1 and 0, the output of the NAND gate should be equal to, so this is 1, this is on, this is off, so nothing really happening here. Okay? So now we change the input to the second input of the NAND gate from 0 to 1. Not the dynamic one, but the second one. We just decide, here's a static gate. We're going to wiggle that other input a little bit and see what's happening. Now, interestingly enough, you can see that this node here is the internal node of this NAND gate, which was originally basically at VDD, is now getting pulled down to 0. This node gets pulled down to 0. Again, we see here a capacitive coupling effect happening. Actually, this capacitor can impact the charge stored at the other input node. That's really annoying, right? You have a gate, a static gate, and you wiggle one input and you change the value of the other input while you're doing that. Just because of the fact that the other input is a dynamic node and charge coupling within your static gate can actually make this thing go back and forth. And to show this is realistic, this is actually exactly what happens. This is SPICE simulation. You see you have your clock, your output is high, output 1 is high. We have some clock feed through, as you can see. The output goes higher than 1. And then we change output number 2 of the static gate, and as a net result, output 1, or the second input of my NAND gate, basically changes and can create all kind of messy stuff. So these are all the type of things that you have to be very wary about when you do dynamic design. So you better stand on your toes and do a lot of analysis and think very carefully about what are the critical nodes, how complex are the couplings into them, and so on and so forth. But if you do so and you spend enough time on it, you're going to be rewarded. It's going to be fast. Right? Nothing comes for free.
Jan, I think in the slide where you show the back gate, right, you should have the output of the second gate should start at 1 and not at 0. In the slide you showed it starts at 0, but you probably then should it starts at 1.
The second output.
The slide previous to this, you see, like you say out 2 equals to 0.
Yeah, that should be 1. I agree. All right, so there's some other problems. I'm not going to talk about them. Don't worry about it. But there's some other concerns that dynamic CMOS guys might have. But there's a last one, I think, which is very important. Cascading dynamic gates. And that's why I really want to talk about a little bit more about the rest of the lecture and also show why this is an important topic. Now it's okay. Static CMOS gates, I want to do complex logic. What do? You start one gate, and you connect it to a next gate, and you can connect as many gates together as you want to. Right? I can make a very deep logic type of network. Now I'm going to try to do this with dynamic logic. So okay, I take one first dynamic gate, and I'm going to couple it to a second one, a third one, and so on and so forth. Should work, right? Well, in reality, it doesn't. It's actually not as trivial. And the reason for that is there's one very, very darn good reason. Remember the rule I said to you? If I have a dynamic gate, what can happen to the inputs of the dynamic gate? During evaluation, they can either stay the same, or they can make a 0 to 1 transition. They're never allowed to make a 1 to 0 transition, right? That's the rule. Now, let's see what's happening if I connect two of those good old gates together here. So this is gate number 1. I say, okay, that's fine. There's one inverter. Let's put two inverters in a row. That's really what I would like to do. Both of them being dynamic. Now, let's think what's happening here. This, at pre-charge time, this goes to VDD, this goes to VDD. Okay? So now I start evaluate mode. Suppose that this is a 1. I apply a 1 at the first input. So you expect output 1 to be 0 and output 2 to be 1. Right? What's happening? Well, I turn on my evaluate devices. And if you look at it, this is a pre-charge node. This is 1. This is 1. Both of your inverters will start discharging simultaneously. Right? This node will go down. And suddenly this node will realize, oh my God, this is 0, this is another 1. It stops, turns off this transistor, but it's too late. Because during that time, we have been happily discharging output number 2. Charge is gone, no way to get it back. Unless, obviously, you have to wait for that bleeder device to pull it all the way back to the level return device, which will be too long. So that's a challenge. That's the problem. Because it shows that I just cannot connect two of those devices together. Because it violates my rule. This node here, from the second inverter, we see actually that there's a 1 to 0 transition going on at the input of that particular node. During evaluation, the input of this transistor, the NMOS transistor, is going from 1 to 0, which is a violation of my rule. And again, just to show it in more detail, that's what you get. So out 1 goes down, and suddenly out 2 stops and hangs somewhere in the middle. And I don't know what I have. And as I said, obviously, the level restore device very slowly might pull this way back up. But that's going to be too slow. So what to do about it? Any idea? Any suggestion? There's a couple of tricks you can use. What would be your first thought? No clue whatsoever? You're engineers, right? You should be able to come up with some little trick. We're good in tricks. Buffer. Very good. That's a very good answer, because that's what most people will do. And actually, that's what I'm going to spend most of my. You basically say, I cannot have 1 to 0 transition, but I can have 0 to 1 transitions. No problem. If I put an inverter in between the two, I'm basically there, right? I basically will have only the one. That's called domino logic, and that's what we're going to talk about next. There's some other tricks I could do, right? If I say, well, if I would just delay this evaluation time of the second one by a bit, if I make it start a little bit later, you could do it as well. But then you need multiple clocks. And actually, that's what people initially did. Designers came up with networks which had 8 different clock phases or something like that. Sometimes 16 clock phases. And they very carefully figure out this one goes first, and then this one, and then this one, and then this one. And this way, they can very carefully manipulate when you turn on the devices in such a way that you don't have that particular effect. But indeed, you're right. The best thing, and there's another one that I'll show you briefly as well, but I'll save that for a little bit later. So, domino logic. Indeed, that's what you do. You take a complex logic gate, and I add an inverter between the two. As you can see, during pre-charge time, this is at VDD, this is at 0. Okay? So nothing now during transition, this stays either during evaluation mode, this stays either at 0, or if this node goes discharging, this is going to go from 0 to 1, which is perfectly legit. We can do that. So by adding this little device here, this inverter, we basically have solved that particular problem. Okay? Now having that inverter is actually good for another thing. Actually, it's good for a couple of things. It makes the addition of our level restoring device easier. Remember, level restoring device, you need an inverter and then a PMOS. Now I have this inverter already there, so the only thing I have to add is this little feedback device. So it really helps making level restoration or bleeding a lot easier. We have it there, so we should do that. Now you might ask yourself why we call this Domino, right? Well, actually, it's quite easy to look at it. By having this inversion, so you pre-charge everything, right? All the nodes are sitting there, 1, 1, 1, 1, 1, 1, 1, 1. And then you start with the first gate, you turn it on. If this thing starts with a 0 to 1 transition, then this is going to go from 0 to 1, enables the next stage, then this one will start working. Oops. And so on and so forth. So it looks like you've probably ever seen this on TV. One of those guys basically built this giant stacks of dominoes all over the place, very long stacks, and you trip one and then it keeps on going and going for half an hour. It's exactly like domino logic. You basically trip the first one trips the second one, the third one, the fourth one, the fifth one, and so on and so forth. And that's the way this whole thing works, so that's why they called it domino logic. It's like a stack of falling dominoes. Okay, very well timed in space. The whole sequence of events is fairly carefully controlled. Now, it has some problems though. By adding this inverter to this gate, we already create something which is, we create a logic family which has some properties that you have to be very much aware of. Remember that a CMOS gate is always inverting, right? Here, we create logic which is always non-inverting. Because you always have an inverting stage followed by an inverter, so it's non-inverting. So if you need something that inverts, we're going to have to add special, basically static logic to it. Maybe extra inverters or something like that. But be aware of that. It's always non-inverting, which makes some hardware basically complex. There's some other tricks which are interesting to observe, though. Something to be aware of. If you now start thinking about the logical properties of this thing, obviously it has all the same properties as dynamic logic. VOL is 0, VDOH is VDD. Now think a little bit about the propagation delay. Okay, propagation delay in one direction is 0, right? When it's high, when you want to go high, basically it doesn't cost you any time, so it's 0 for that. For the other direction, it's a high to low transition, right? So we're going to take this node and discharge it to low. Okay? Now, and then we're going to propagate this to this inverter. So we know that during evaluation mode, this node will make only one type of transition. It either stays at high or it goes from high to low. That's an interesting thing to know. I only really care for speed perspective. Pre-charge is another thing, right? Pre-charge is a different phase. But for basically evaluation mode, we see that this node will make only one transition. How could I use this thing to make my gate overall faster? If I know that, right? They say, I don't care about the low to high, but I only care about the high to low transition. How could I do this to make the overall propagation delay of this structure faster? We really worry about the inverter, right? There's an inverter sitting behind it. What would I do with the inverter to make it faster now? Now that I know, they have to only make a high to low transition. What can I do with inverters, right? Sizing the transistors. How would I size it? Where would I like to be the switching threshold of that inverter to be sitting? In the middle? Sure. Remember, you're sitting at VDD, and you see something going down. You want to get that, when it started going down, you want to get an inverter behind it acting as soon as possible. You say, okay, we're going down, let's get going. So I want to move the switching threshold actually higher up, because I really want to make that next inverter to start acting as soon as possible, because that's really the transition I care about. The other transition I don't care about because it doesn't happen, unless it's in pre-charge mode. So what we're going to typically do is skew this inverter by making the PMOSs bigger than you normally should. We move the switching threshold up. And by doing so, we speed up this device again. Right? There's a very common trick in dynamic logic, definitely in domino logic, is use skewed inverters to basically speed up the device again. Okay. Time for normal logical effort exercise. We seem to love this. We do this for every logic family, so let's do it for this again. Let's see where we end up. So let's first start with the case that I don't skew the inverter. So here, oh, by the way, there's one thing before I go there. There's one more point that I'd like to point out. One other good feature of domino logic that you wouldn't have with normal dynamic logic. Look at the gate, very complex gate, like this one here. Oops. I have to go all the way back, Here. Nope, not there yet. Like this one here. Complex logic network. Obviously, suppose now that I have a large fan out here. This thing, discharging a large capacitor is not a good idea, right? It's a lot of effort because you have a lot of transistors in sequence here. You know, discharging a very large load capacitance to a complex logic network is not a good idea. Remember, about 5-6 lectures ago, we talked about what you would do in a case like that. Trying to size up all your transistors in a complex logic network to drive a large capacitor is not a good idea. Typically, we would use the divide and conquer approach. So it's better to add a buffer in between and let the buffer do the work of driving that large capacitance. And then we can optimize this network for maximum speed of the logic network. With domino, we get this automatically. We have the buffer there. We can size the buffer to drive the fan out without impacting the complex logic network. So this has this automatic divide and conquer thing that we so like. All right, this is the whole class in a really fast playback mode. Okay, we're back at logical effort. So let's think about this thing for a second here. So you have an inverter. Logical effort of the inverter, when right? So we know that. Logical effort is 1. So by adding this inverter, we don't really change the logical effort of the whole chain. It stays the same. We multiply it by something which is equal to 1. The logic network of this one here, you have an AND gate, 2 transistors in series. But remember now, we also have that extra evaluation transistor, which is going to hurt us a little bit. So we have to size up all the transistors with a factor of 3. So if you think about this, the total capacity is here. This is 3 over 3. Remember, normal inverter. Oh, wait a second. This is an AND gate for normal. Yeah, compared to an inverter, this capacitance is 3. Logical effort of this thing. This also sees 3, so this is 1. So the total logical effort of this thing is 1. See that? Right? This is 3 over 3. Normal inverter, as you remember, for logical effort, you compare it with normal inverter, which has 2 plus 1. That's 3. Here I see 3 as well. So we actually have built now a 2-input NAND gate, which has the same logical effort as a single inverter, which is nice. That's a gain. Okay? It even gets better when I do NOR gates. Because in NOR gates, I don't really have to have I don't have any transistors in series. So this is 2, this is 2. Again, I double all the transistors because I have this evaluate transistors. So the capacity, this is equal to 2 over 3. So my total logical effort is 2 over 3. While if I would implement this in a static logic, you get a factor 7 over 3. 7 over 3, that's a factor of 3 times better than the static implementation. But remember, in a static mode, NOR gates, not good. We like NAND gates. In Domino or dynamic logic, this is the preferred mode. Right? Better than this instant thing. NAND gates are not as good in dynamic logic as NOR gates. Avoid series of transistors, obviously. Okay, but that's a pretty nice gain. Even with that extra transistor, we still have a very nice reduction in logical effort. Now, the situation gets a little bit more complex when I start doing skewing. Suppose now I say I'm going to skew this device. Okay, I'm going to make it, let's say a single inverter here, single input. I'm going to make the PMOS double the size of what it normally would be. Okay, now it's let's look at what we would get. Well, for the inversion part here, that is equal to 2 over 3. Now, the logical effort of the inverter here, that's a little bit trickier to figure out because you have to look at the direction. If I would like to have a reference inverter that would have the same type of performance in the pull-up mode, right? That's really what we're worrying about, pulling up the thing. So this would be 4 over 2. Right? If I really want to get in the same direction, this is transistor 4, this is the same 4 here. If I want to get the same effort, I would have 4 over 2 there. So this total capacitance is 6. This is 5. Okay? So this is 5 over 6. And you multiply the 2 together, I should get 10 over 18. This for an inverter. And same result shown here. 5, 6, 2/3, 10, 18th. Actually, it turns out that very interestingly, I put 2 gates in sequence here. An inverter, a dynamic inverter followed by a skewed CMOS inverter. And the net effect is something which has a logical effort which is smaller than a single inverter. That's quite beautiful. It's a very interesting result to have. 2 gates in sequence better than one, and 1 gate in sequence of which one of them has exactly the same composition. So that's why this whole trick with Domino CMOS is so nice. It's very fast because of that particular effect. We really managed to get logical effort all the way down. Okay. Now, designing with Domino logic, we can now, this is the basic gate. But I can do some other funny things. So, okay, I really want to make it even faster. Right? We're now really in this space that people worry about picoseconds. Speed is the ultimate thing in their life. They're going to do anything to squeeze out a little bit more. One thing that's really annoying in Domino logic is this guy here, right? That footer device. If I could make that footer device rid of that footer device, I can make this transistor twice as small, which once again would reduce my logical effort with a factor of 2. That would be a good thing to do, but it's not very healthy to remove that footer device. Remember, during pre-charge, you will have leaking all over the place. Right? If you don't know what the inputs is, or you have to control the input, basically pre-charge wouldn't work, basically. So you need those devices to make pre-charge to work. Now, how to do that? Well, obviously for this gate, there's not much I can do. I have to have that footer device sitting there. By the way, this is called a footer. The other one is called a header. Foot transistor is something that connects to ground. A header device is something that connects to VDD. Non-common terminology. I forgot to introduce it to you. So, however, one thing we know, if when you pre-charge this, this goes to 1. And since this is Domino, this goes to 0. So it means that all the inputs, if I'm really careful, if I can manage to set all the inputs during pre-charge, if I can manage to bring all the nodes that are input to a gate to 0, then that pull-down network for sure is going to be off, right? It's an NMOS network, all the inputs are 0, network is off. In that case, I can get rid of this transistor, right? If I just ensure that all the inputs are 0, we're fine. So this can be done quite nicely. If I basically make sure that all my primary inputs, the first gate in the network, always going to have a footer device. We need that there. Then we ensure that all the other inputs during pre-charge are all going to be 0 eventually. And I can get rid of the footer device, which means that during evaluation, all those extra gates are going to be darn fast. Another performance gain I'm getting. Okay? So that's kind of shown here. You have a fairly complex network with a lot of gates in a row. This one here, we have to make sure that we have a footer device here. We cannot avoid it because I don't know exactly what the input would be. If I could force the inputs to be 0 during pre-charge, I would be fine. But you might not know. It might come out a register, it might be a 1 or a 0, we don't know. So there I put a footer, but for all the other device, I basically get rid of it. And I can just have a very simple type of network. You have n+1 transistors per gate instead of n+2. Very clever trick. But you have to be wary about one thing. Right? Suppose we do something like, we have logic here. And suppose by accident here, some of them are 0, some of them are 1, whatever happened. Something happened during my previous computation. Some of those outputs are going to be 1, some of them are going to be 0. Right? So when I now start turning on this device here, and I turn on all my pre-charge devices, all the pre-charge devices go on simultaneously, right? They have one clock signal coming in, bingo, all the gates start pre-charging. But if it happened that one of those guys still has a 1 at its input, it will start leaking. You start trying to pull it up, but at the same time the NMOS is still on, till the previous node got pre-charged and say, hey, no, you have to be a 0. So the pre-charge will actually start rippling through from the beginning towards the end of the chain. Right? And that's a problem. Because now you can imagine that during that period of time, there's going to be current flowing to this network. So pre-charge might take quite a bit of current. Also, pre-charge can take some time now, because you start pre-charging the first one, then the second one, the third one, the fourth one, the fifth one. You have the same type of propagation delayed effect that start happening to the pre-charge. And your pre-charge time may start to get quite long. Okay? So that's the problem with this. It's really zippingly fast during evaluation, but you might have some problem with pre-charge because it's rippling, and we might have short circuit current flowing while that ripple is happening. Right? So what do you do about it? Well, like any good engineer says, this is really cool, but I cannot afford that. Yeah, it's nice and fast, but let's backtrack a little bit. So what I could do is, for instance, say, maybe what I can do is have one gate with a footer device. Let's see if I can find something here. One device with a footer device, the next one no footer device. And to avoid the ripple, I'm going to break it up again. I'm going to put a footer device on the next one. I'm going to ensure that is fine, and so on and so forth. So you kind of alternate devices with footers and without footers. And this way, you avoid some of that short circuit current effect. Because the path, the rippling path, is now going to be only 2 gates deep. You pre-charge this thing will shut off real fast. All right, so it's a combination of factors that you can play. Okay? This is called a variant of footless domino. Another thing you can do is based on what I already mentioned before. What I could do actually is, remember that when I said one way to get around this problem of the 0 to 1 transitions is to delay the evaluation phases of the different nodes. I could do the same thing with the pre-charge. If I just say, okay, I'm going to start pre-charging this one first, bingo, pre-charges. We know that this thing at a point in time is going to be at 0, so this device is off. Then I can turn on the pre-charge of this guy. The same thing here, then I turn on the pre-charge. So I just put some delay in the clock network between the different stages. And then I can avoid having any footer devices altogether. You just very carefully time when your pre-charged clock arrives at any one of your pull-up devices. Very simple trick, works quite nicely. But again, this is something that you better analyze. This is not something that you can put in a standard cell library and say, hey, do this automatically for me. Right? You have to work on it. Okay, so we're almost done with Domino, with basically Domino logic. Like there's differential static logic, obviously they also can make differential domino logic. What we could do, for instance, is something like this, is I have a pull-down network, inverted pull-down network, pre-charged transistors, one footer device. And like before, now basically doing level restoration is not that hard. I can cross-couple the outputs to each other, like we did in CPL. In some sense, this looks very much like CPL, but instead of connecting this this bottom line here to an input, we just connect it to ground. Simone? Yes. Actually, it's used in a small variant. And the variant is as follows. It turns out that when I make these complex networks here, there's actually a possibility, you do it very cleverly, there's a way for me to actually even extract intermediate outputs of this network and also use them as outputs. If you pre-charge them right, you can actually have what's called multiple output differential domino logic. So people play around with that. Again, used, question is all what does used mean, right? Is it 0.01%? Yes. It's not used in massive numbers. But yes, it's a very nice logic farm. And there's one place where it was used very often. Actually, where the main reason why this thing became popular, it's going to bring me a little bit further. I'm just going to give you one word about it. Why this was popular for a while. And some people, some designers still use it. Can we switch to the overhead camera, please? Okay. Typically logic, this is kind of a little sidetrack here. Typically logic, the way you operate logic is, okay, I have registers and I have a clock. And then I clock the registers and brrr, my logic works. And then suddenly I wait long enough, everything is done. And I have another row of registers and I clock the results in the next latches. Right? So the way the separation between the clocks is going to be determined by the longest path through all that logic. Right? The worst case path. Okay? And that's what we typically do. We do worst case design. You look at over all the possible input patterns you have, and the separation between your clock periods has to be the one that basically ensures that the result is always going to be completely finished. Right? Now, wouldn't it be nice if I would have a signal that says, I start my clock, or my input signal, I say, okay, start computing. And it goes through logic, and suddenly it says, I'm done. I'm finished. Wouldn't that be nice? That logic tells you automatically, rather than having to wait for basically do a lot of simulation and say, well, gee, that's my worst case delay. Now, if the logic itself would tell you that it's finished. Auto-completion, basically. Now, that sounds like a fun idea, but how will you do it? Well, with dynamic logic, it actually works quite nicely. Or differential dynamic logic works quite nicely. So suppose I have this. So this is pre-charge, PMOS, PMOS. And I have this two shared and NMOS divided to ground. So this is clock. I call it clock for the time being, but you might want to call it enable, clock, and clock. And this is out and out bar. Right? Differential logic. This is differential dynamic logic. These are pull-down networks. Somebody's giving me a message here that I'm going to turn off. Okay, so this is this is exactly what I showed you before in a somewhat more schematic diagram. Right? So what's happening at the end of pre-charge phase? We know that this thing is going to be 1. This is going to be 1 as well. Right? We have pre-charged both output nodes. During evaluation mode, we know that 1, but only one of those output nodes is going to go to 0. Right? That's because it's differential. So one of those nodes will go to 0. The other one stays at 1. So when is completion now happening? Well, when one of those outputs goes to 0, we know that you're done. So if I now take the two outputs of this thing and OR them together, or XOR them, one of them is fine, it doesn't matter. What I have here is a completion signal. Because initially this is 1 as 1, well, let's make it an OR. I think 1 is 1, this will be 1, and from the time this one of those changes, this will go to, this will be 0. If one of them changes, the output will go to 1 and say, I'm done. So if you now put a long chain of gates like this together, you can actually have a complex network. Out of the last one, basically, we see one of those 1 to 0 transitions. Remember, in dynamic logic, you can have only one transition per evaluation period. So if I take somewhere the output signal, I XOR or NOR the two outputs together, I get a completion signal out of this. I say, okay, I'm done. I can start with the next one. I don't have to wait for a long spot. So the advantage of this approach is now that I can compute not at the worst case speed, but at the average speed, which potentially makes you something faster. This is called self-timed logic, which is not a topic of 141. It's a 241 material, that thing. But this is where this logic family was but a lot of people used differential dynamic logic, domino logic exactly for that reason. Okay? So that was a long answer on a short question. Okay, good. There's one more thing I want to do before we quit. We have 1 minute left. I want to show you one more approach to avoid this problem that I showed you with cascading dynamic gates. Remember that when I introduced dynamic logic last class, I said that you can do this with NMOS pull-down networks, where you have a evaluation transistor at the bottom and a PMOS pre-charge transistor on the top. So when you pre-charge this thing to 1, right? And evaluate, basically, we either stay at 1 or at 0. So this is the events you can have at the output of this node are 1 to 1 when nothing happens, or 1 to 0 when we discharge the node to ground. Now, I mentioned to you that I also could build the dual gate, where I use a PMOS pull-up network with an evaluate transistor on the top and a pre-charge NMOS device on the bottom. So what's happening during pre-charge here is that I pre-charge this node to 0, and the only transitions that I can have is this node stays at 0, or you have a during evaluation, I'm going to charge up this node to VDD when this network is enabled, right? Now, you can imagine for this pull-up network, during pre-charge or during transition, here the rule was that only, for this one, I can have only 0 to 1 transitions at the input, right? That's what we said. During evaluation, we cannot have a 1 to 0 transition, because then we lose charge. Same thing is true here with the pull-up network, but just the opposite. Here we can have only 1 to 0 transitions. So it means that if I look at this can have 1 to 0 transition. This allows, those things can be coupled perfectly. I can have an NMOS network, followed by a PMOS network, followed by an NMOS network, by a PMOS network, and so on and so forth, without inverters. So that's quite beautiful. Actually, it turns out that I can either get around this extra inverter of this domino logic by just alternating PMOS, NMOS, PMOS, NMOS, PMOS, NMOS. This is called NP CMOS, and is the core of a logic family which we'll discuss briefly later, which is called NORA. And NORA stands for no race. But remember, you should remember this, because it's a simple trick that sometimes comes in handy. It allows you to eliminate some transistors, and this is zippingly fast. The only problem is you have to be a little bit careful. The pull-up network is PMOS transistors. You don't want to stack too many PMOS transistors on top of each other, because that's slow. But if it's shallow, like a NAND gate, this thing would do quite well. Okay? All right, that's it for today. So we'll see each other again on Friday.